For this video, I'll be going through Pure Physics, Chapter 18, Electromagnetism, Success Criteria C. Describe experiments to show the force on a current carrying conductor, and on a beam of charged particles in a magnetic field, including the effect of reversing the direction of the current or the direction of the magnetic field. So we have learned in previous chapters that whenever a current flows, so when current flows, it will produce magnetic field around it. Now how about if we have two current carrying conductors? That means the current or we have two wires that have both currents flowing through them, and that means there will be two magnetic fields produced, right? So if two parallel wires, each carrying a current, are brought closer, the two magnetic fields of the wires will interact. So this is like your magnets. If there's only one magnet, this magnet of course will have a magnetic field. So coming up from north, the field lines, and entering the south. But because this is its own magnetic field, there will be no interaction with other magnets. However, if I were to put another magnet near it, so this is south and north, and again there will be magnetic fields produced, and because the magnetic fields will interact with one another, the field lines will interact with one another, so therefore it results in a resultant force whereby we have two magnets, they will either attract or repel. So similarly, now our current carrying conductor, they are acting like magnets. They are acting like magnets because they are able to produce magnetic fields. Hence the name of this chapter is electromagnetism. So coming back to this, the magnetic fields of these two wires which are carrying current and producing magnetic fields, the magnetic fields will interact and produce a combined field pattern as well as a resultant force, right? Just like two magnets whereby you put them close together, they will interact and then there will be a resultant force between the two magnets. So the type of the magnetic field pattern and the direction of the force depends on the direction of the current. So it's important to note that whenever two magnetic fields interact, a force is always produced. So now we take a look at this example. We have learned in the previous success criteria about our dot and cross. So let us try to practice it now. So these two straight lines, they are actually the wires. They are the wires, and we are looking at the wires from the top. That means if I were to draw a top view, I would actually see two circles. So the wire on the left is having current going from bottom to the top. So it's sort of entering the eye. Therefore, I'll be using a a dot. Whereby for this, the current is actually so I need to make an amendment here. I need to change the wire, the current's direction, for this to be going down. And this will be going up. So this one you might want to change in a note so as to not have confusion. So if I were to do this right, then the left wire will have a cross, right? Because the current is going away. The current is going away from the viewer who is viewing it from the top. So it will be a cross, and on the right, the current is going towards the viewer, so it will be a dot. So if it's a cross, right? I think something wrong with this diagram. So if it's a cross, maybe we don't care about this. So if it's a cross, then we have to apply our right hand grip rule for straight wire, whereby the thumb represents the direction of the current. So the one on the left, you should have your thumb pointing inwards. Therefore, the magnetic field will be in a clockwise direction. In a clockwise direction. Then the one on the left, so your thumb should be pointing to yourself because the thumb represents the direction of the current, and your thumb should be pointing to yourself because it's a dot, right? So it should be this direction. Okay. So because the magnetic field lines over here are in the same direction, they are in the same direction, and remember, magnetic field lines, they cannot cut each other or touch each other. That means it will go on to look something like this. Okay, so this is the direction of the magnetic field lines. Okay, something like that. Then on the right hand side, it is a dot. So the magnetic fields will be in a anti-clockwise direction. Okay, and because in between, the field lines cannot cut each other. Okay. Yep. So this will be the resulting pattern. Okay. Then how about now we switch the direction of the current. So this one is correct. Okay, we make it that the current is flowing towards the user. The current is flowing towards the user, therefore it will both be dots. Okay, so if it's a dot, then the direction will be like this. Okay, and this is towards here. Okay, so in between here, take note, because the direction of the magnetic field lines are opposite to one another, so therefore they will cancel each other out. But if you look at the previous one, whereby the currents are in opposite direction, the magnetic field lines in this region, they are in the same direction, so there's no cancellation whatsoever. Okay, and furthermore, over here, it is in this direction, right? So it will naturally form this shape here. Okay, so it looks like a peanut shape. Okay. Okay, then what happens if I have a current carrying wire and an external magnetic field? So just now we did actually two wires that have current flowing through them. Now we are doing one wire carrying current, and it is now placed inside a external magnetic field. So this current carrying wire will produce a magnetic field, and this external magnetic field, of course, there's a magnetic field. So due to the interactions between the magnetic fields, okay, then there will be a force. Okay, so we actually have this diagram here. Okay, so remember, the magnetic fields always goes from north to south. So for this, external magnetic field is downwards. Okay, so if I were to draw a side profile like that, the north to south, I'm looking at it this direction. The direction of the magnetic field for the external magnet, right, it is from the top to the bottom, from north to south. And if I'm looking in this direction, I can see the wire as a circle, right? And if I were to close the switch, the current here is positive. Sorry, over here, this terminal is positive, so the current will flow this way. So as it flows down, it will move away from me because I'm viewing in this direction. Okay, so it will be a cross. So if it's a cross, then the direction of the magnetic field will be in a clockwise direction. So you need to apply your right hand grip rule for straight wire. Okay, and your thumb, which represents the direction of the current, should be pointing into the screen. Right, so it will be a clockwise direction. Okay, so maybe I can explain why there will be a force. Okay, so firstly, why is there a force? It's because due to the interaction of magnetic fields. So I need to emphasize the S here, because there must be two fields or more for them to interact. If it's just a single field, that means if I just have this wire carrying a current, it will produce a magnetic field, but there will be no interactions because there is only one magnetic field. So if I have a magnet here, so of course it will produce magnetic field, okay, but there will be no interaction with the other magnetic fields, because if I just place a magnet there, so the magnet will just stay stationary, there will be no movement. However, in this example, we have a current carrying conductor placed in an external magnet. Okay, so both of these will produce magnetic field, which will then interact, and then they will interact and they will produce a force. Okay, so why is there a force? Because of the interaction of the magnetic fields. Now we can explain or we can use the interaction of the magnetic fields to predict the direction of the force. Okay, so let's say the magnet is very heavy and it doesn't move, right? So the wires can actually move. So let us take a look at how we can use magnetic field lines to tell us what's the direction of the force. So if you look on the left hand side, the magnetic fields, which is the black color one produced by the external magnet, and the purple colored magnetic fields, which is produced by the current, they are in opposite direction. So if they are in opposite direction, they will cancel each other out. So can I say that originally, okay, there are two magnetic fields, but because their directions are opposite, they cancel each other out, so there is zero magnetic fields. Okay, there are zero magnetic fields. Okay, then if I were to look at the right hand side, so there are two magnetic fields. One is the black one produced by the magnet, okay, is going downwards, and the purple magnetic field produced by the current carrying wire. Okay, so there are two magnetic fields, but because they are in the same direction, okay, they will actually reinforce each other. They will not cancel each other out. So I will say there will still be two magnetic fields. Okay, so the direction of the force is from more to less magnetic field. More to less magnetic field lines. So it will go from 2 to 1, 2 to 0, I'm sorry, 2 to 0, and therefore the wire will swing this way. Okay, will swing this way. Maybe I can try another example whereby I keep the magnet the same, and the magnetic field is always from north to south. Okay, now if I have a wire over here, it carries a current, and now the current flows in this direction, okay, towards us. So how would we draw the magnetic field lines? So the thumb will represent the direction of the current, and now the thumb, if you are looking at the screen, your thumb should be pointing to yourself, and if you are using the correct hand, which is the right hand, okay, the direction of the magnetic fields will be in anti-clockwise direction. Okay, anti-clockwise direction. Okay, so in an anti-clockwise direction, and we see that there are more than one magnetic field. One is the black one, and the other one is the blue one. Okay, and due to the interaction of the magnetic fields, there will be a force exerted. Okay, so let's look at the area on the left hand side of the wire. Okay, there are two magnetic field lines and they are in the same direction. Okay, so if they are in the same direction, they will reinforce each other, and therefore there will still be two magnetic field lines. On the right hand side, the magnetic field lines are opposite to one another. The blue one is going to the top, the black one is going to the bottom, so they will cancel each other out, opposite direction, so they will cancel each other out, so therefore there will be zero magnetic fields, and the the direction of the force is always from more magnetic field lines to less magnetic field lines. Therefore the force on the current carrying conductor will be to the right. Okay. Okay, take note, if the connection of the terminal is reversed, right, that means the current flows in another direction, the wire will swing in the opposite direction. Now, if the polarity of the magnet is reversed, okay, the wire will also swing in the opposite direction. Now, if the strength of the permanent magnet is increased, or if the current in the conductor is increased, a larger swing will be produced. Okay, so this is what happens. The wire will actually swing inwards or outwards. So depending on the direction of the current will swing either in or outside. Okay, so why is it that when this coil sort of swing outwards, okay, it will swing back? Is because when it's outside, it will not be within the influence of the magnetic field of the external magnet. So even though current is flowing, there is no interaction. Therefore, it will swing out and swing back in again. Okay. So let's read this. When a current carrying conductor is placed in an external magnetic field, the conductor will experience a force, right? Due to, this is important, interactions of the magnetic fields. Okay, so again, I emphasize the fields, right? There must be more than one field, and then they will interact with one another. Okay, so this is the explanation. So take note, this is the current is flowing into the page. So practice using a right hand grip rule for solenoid that the direction of the magnetic field produced is in a clockwise direction. Okay, and we have a magnet, external magnet. The direction of the magnetic field is north to south, so it's going upwards. Okay, so if this is now placed in the magnetic field of the external magnet, so if you look at this on the left hand side, okay, we have them flowing in the same direction. So we have more magnetic field lines. On the right hand side, because it is supposed to be in a clockwise direction, so it's going downwards, but the external magnet, its magnetic field lines are going upwards, so they will cancel each other out, so we have lesser magnetic field lines. So the force will be from more magnetic field lines to less magnetic field lines. Okay, so take note, the force acting on the wire is always from a region of more magnetic field lines to a region of lesser magnetic field lines. So is this the only way to sort of know the direction of the movement? Is this the only way to know the direction of the force that's applied on this conductor? No, because later we'll be doing a Fleming's left hand rule, but that will be covered in success criteria D.